Good morning, students. In the previous class, we were discussed about Biot-Savart law. I hope all of you learned the topic very well. Today, we are going to discuss one of the most important topic in that lesson, that is magnetic field along the axis of a circular current loop. We can expect this question in your board exam. Let's start our class. So first you have to consider a circular loop. So this one is circular loop. And you have to take the approximation that this circular loop is perpendicular to the plane of the paper. So like this one. So this is a circular loop. This circular loop is perpendicular to the plane of the paper. Okay. Then we have to assume that the radius of the circular loop is A. Okay. Then we wish to find the magnetic field at the point P. So because this is a circular loop, then what happens when current is passing through the loop, a magnetic field is developed. So you have to find out the magnetic field at an axial point P. Axial point P at a distance R from the center C of the circular loop. Okay, so first you have to consider a circular loop of wire of radius A and carrying current what? I. Okay, the loop carrying current I. Let the plane of the loop be perpendicular to the plane of the paper. Okay, then you have to find out the magnetic field at an axial point B at a distance R from the center of the loop. Okay. So first you have to consider a small element dl. Okay. Suppose this is a circular loop. First you have to consider a small element dl. A current element dl at the top of the circular loop. Okay. So here this one is a dl. This is the current element dl. So first you have to consider a current element dl at the top of the loop. Okay. So here the current is an outward coming current. So the direction of the current is outward coming current. Okay. So the direction of the current is towards you. So this is a circular loop. So in this circular loop the current is outward coming current. Outward coming current means the direction of the current is towards you. The direction of the current is, this is the circular loop. So the direction of the current is towards this small element. The direction of the current is towards you. Okay. The what about at the bottom? This is inwards the paper. That means it is towards the paper. Okay. So we have to consider a small current element at the top of the circular loop. The direction of the current is an outward coming current. Okay, the direction of the current is an outward coming current because you have to consider small element here. And also one more point, if vector S be the position vector of point P related to the element dl. Okay, so vector S. So what is vector S? Vector S be the position vector of point P related to the element dl. Okay, then you have to consider the Biot-Savart law. Okay, so you have to apply the Biot-Savart law. Savart law here. So what's the Biot-Savart law? That is dB is equal to mu 0 by 4 pi I dl sin theta divided by what? R square. Okay. So here what's the equation of Biot-Savart law? That is dB is equal to mu 0 by 4 pi I dl, that is current element, sin theta divided by what? Here the I dl and P is the, what's the position vector here? S. So it is S square. Okay, so apply the Biot-Savart law. So dB is equal to what? Mu 0 by 4 pi I dl sin theta by S square. Okay, then you know that according to Biot-Savart law, dl and S are perpendicular to each So since here dl perpendicular to s, because here the current element its direction is perpendicular to s, because it is outward coming current, so its direction is like, okay, and also the position vector is perpendicular. Position vector is perpendicular to this current element. Okay, position vector is perpendicular to this current element. So what happened? DL perpendicular to what? S. So what happened? Theta is equal to 90 degrees. So what happened? Sin theta is equal to 1. So the dB is equal to mu 0 by 4 pi I dl divided by s square. Okay, dB is equal to mu 0 by 4 pi I dl by s square. Then the field dB, again you see the diagram. So here where is dB? So the direction of dB is also perpendicular to s. How to apply? You get the direction of current is perpendicular to s. That means the direction of current is this direction. That is, this is dB. Okay. Then here marked as, this one is Q. Okay. So the direction of dB is perpendicular to s. Okay. Then you have to resolve dB into two rectangular component systems. Then you have to resolve dB into two rectangular component system. Then you have to resolve dB into two rectangular component systems. Okay. So dB sin phi along the axis. That is dB sin phi along the x-axis, and dB cos phi perpendicular to the axis. That means dB cos phi along the y-axis. Okay. And also how to find out the magnetic field dB at the bottom of that current carrying circular loop. Okay. Also we get the magnetic field dB, and also the resolve dB into two rectangular components. Again we get dB sin phi along the x-axis, then dB cos phi along the y-axis. Okay, because these two are two diagrammatically opposite elements of the loop. So for any two diagrammatically opposite elements of the loop, the component perpendicular to the axis of the loop, that means dB cos phi, the component perpendicular to the axis of the loop will be equal and opposite and will cancel out. That means dB cos phi is cancel out. Okay. So here dB cos phi will cancel out. The axial components, that means dB sin phi. Okay. So dB sin phi will be in the same direction, that is in the which direction? In the CP direction. That is in the CP direction. dB sin phi along the CP direction. So it is added up. Okay. So dB cos phi are equal and opposite, so they cancel each other. Then dB sin phi what? Added up. Okay. So the total magnetic field. So you have to find out the total magnetic field. So what is total magnetic field here? Total magnetic field. How can you find a total magnetic field of a circular loop? Can you find a total magnetic field? Total magnetic field B is equal to, how can you find a total magnetic field of the circular loop? You have to integrate dB. Okay. dB what? dB sin phi. So total magnetic field B is equal to what? Integral of dB sin phi. Okay. And again you see this picture. Sin phi. From this diagram you have to find out sin phi. Okay. So here this angle is phi. So what about this angle? This angle is also phi. So from this diagram you have to find out sin phi. So what is sin phi? So sin phi is sin phi. Sin phi is what? From this diagram you have to find out sin phi. Sin phi is equal to what? 8 divided by what? 8 divided by s. Okay. So sin phi is equal to what? Sin phi is equal to 8 divided by s. Okay. And also you know that dB. What is the value of dB? dB is equal to mu 0 by 4 pi I dl by s square. You have to substitute these values in this equation. So which is equal to? B is equal to integral of dB is what? Mu 0 by 4 pi I dl s square. Then what is sin phi? Sin phi is A by S. Then tell me which are the constant terms in this equation. Mu 0 by 4 pi is a constant term. Okay. Then what about I and A? This is also a constant term, so you have to taking outside. You have to integrate only dl. This is the changing term here. Okay, current element, which is equal to what? Integral mu 0 by 4 pi I A divided by S cube, integral of dl. Okay, then what about dl, integral of dl? So here we have to consider only a small element dl. Okay, then what about integral of dl? Integral of dl means it is circumferences of the circle. Okay, so what's the value of integral of dl? Integral of dl is equal to, integral of dl is equal to circumferences, which is equal to what? 2 pi into radius, 2 pi into a. Okay, then substitute this value, which is equal to what? Mu 0 by 4 pi I into a by s cube. Then integral of dl means 2 pi a. Okay, then which is equal to what? Mu 0 by 4 pi I a square 2 pi divided by s cube, which is equal to what happened? Here 2 and 4 cancel, then pi cancel. So value is mu 0 I a square divided by what? S cube. Okay, then again s cube can be rewrite in terms of s and r. Okay, s cube can be rewrite in terms of s and r. So see this diagram again. So r is the distance between the point P and the center of the loop, and a is this radius, and s is this what? Position vector. Okay, so what's the relation? You have to apply the Pythagorean theorem. So what is s? S is equal to what? S is equal to, sorry, s square is equal to what? A square plus r square. So what about s? S is equal to a square plus r square raised to 1 by 2. So what is s cube? S cube is equal to a square plus r square raised to what? 3 by 2. Okay, so substitute this value here, which is equal to mu 0 I a square divided by what is s cube? S cube means what? So here also one more term, 2 is also present. 2 is not cancelled. 2 into what's s cube? S cube means r square plus a square raised to 3 by 2. Okay, so magnetic field B is equal to what? Mu 0 I a square divided by 2 into r square plus a square raised to 3 by 2. Okay, so here you have to consider only the one coil. Okay, if we consider n number of coils, that is capital N turns. Okay, then what about the magnetic field B? B is equal to n into mu 0 I a square divided by 2 into r square plus a square raised to 3 by 2. Okay, so this one is the magnetic field along the axis of a circular current loop. So how can we return in vector form? Then you have to put the vector notation, and also the direction is I cap. So next we have to consider special cases. So first case, at the center of the current loop. So for the first case, at the center of the current loop, that the point we have to consider at the center of the current loop, that is P. This point P is at the center of the loop. Then what happened to R? R becomes 0. In that case, R is equal to what? 0. So what happened to this equation? So here R equal to 0. So you have to rewrite this equation as n into mu 0 I a square divided by 2 into R0. So a square raised to what? 3 by 2. So 2 cancel. So it becomes a cube. A cube and here a square. So what happened? A square, a cube cancel. We get only a. That is B is equal to n mu 0 I divided by 2a. Okay, at the center of the loop, the magnetic field B is equal to what? N mu 0 I divided by 2A. Okay, then second case we have to consider the axial point lying far away from the coil. The axial point lying far away from the coil. Far away from the coil. That is, R is very greater than A. Okay, so the axial point lying far away from the coil means R is very greater than A. So here what happened? R is very greater than A. So you have to neglect the term A. That means radius. So what happened? This equation. So B is equal to what? B is equal to mu 0 N mu 0 I A square divided by 2 into, from this equation I will neglect A. So what happened? R square the all raised to 3 by 2. So again 2 to cancel. So N mu 0 I A square divided by 2 into R cube. Okay. So this is at the axial point lying far away from the coil. The equation becomes N mu 0 I A square divided by 2 R cube. Okay. Then one more special case. Third case, at the axial point at a distance equal to the radius of the coil. The axial point at a distance is equal to the radius of the coil. That means R is equal to A. So what happens to this equation? So B is equal to what? N into mu 0 I A square divided by 2 into, here R is equal to A square. That means R square plus R square raised to 3 by 2, which is equal to what? Sorry, we can rewrite as A square. Okay. So N mu 0 I A square divided by 2 into A square plus A square raised to 3 by 2. So N into mu 0 I A square divided by 2 into A square plus A square what? 2A square raised to 3 by 2. Okay. So which is equal to what? N mu 0 I A square divided by 2 into 2 raised to 3 by 2, then A cube. Okay. So which is equal to N into mu 0 I, that is A square A cube. So A square is cancelled, divided by 2 into 5 by 2 into A. This is the equation. Okay. When R is equal to A, R is equal to, the magnetic field becomes B is equal to N mu 0 I divided by 2 raised to 5 by 2 into A. Okay.